clear? I think it's clear. So I'll proceed now. Okay, next task. So the next thing that we will do is that we're going to add a math function, since we are going to square the value of your input. So V is representing a certain or your velocity, and it is represented in your sine wave. So what we're going to do is that to satisfy this equation, we're going to add a math function. This will square the value of your input. So, and then you click on the surface, and you should choose square. And to connect them, you can just drag it here. Okay. And then let's click submit. So now our next task is we need to multiply the alpha to b squared. So we can do this by using the gain block. So we're going to set the gain value to 0.05. By the way, you could just use your interface here, your screen, and then double tap and type in the block that you wanted to access. Then you click. And then to change the value, just double click it as well. And then set the discrete value that you wanted to add. And then it also asks us to connect be automatically connected. So same thing, we'll just need to drag here. So you want to represent or shown your value, you could just adjust the size of your gain. Then drop here, and then let's click submit. So we already obtained the function that we try to represent, right? So let's click next. This task. Just close this one. And we're going to the identifying blocks and signals. Okay. So here we have another function representing the cruise control system. So this is what is modeled here. So it contains a block label, cruise control. We have the PI here. And then so these dynamics are similar to those of the following objects that we previously created. However, the drag force is linearly related to the velocity, and there is an external input instead of gravity. So we have U as our input. So we're representing a control system here. And then what is missing is the input. So the desired speed of the car. And then we're going to add that. So using the step block. So we're using the step block because we're representing a discrete input value. So you could go to library browser, and then like I did earlier, you could just drag and drop the block. But for now, we're just going to type in the interface because it's much easier. So let's just connect. And then, of course, we're going to connect the velocity to the signal assessment. Oops. And we're going to click the submit. So Simulink hides the default names of block. Clicking on the block will show the name, right? You see the step. So we could customize the name of the block. So you could just click here and then you could just rename. So double tap and then just write your desired input name and then desired speed. So we just input desired speed here uh, as the task specified. So, but if you're doing your model, you could create or you could input any names. Then next is hide this. Hindi pa pala ako nagte-next task. Sorry for that. So next is signal can also be named. So we could double click if you want to. So our task is the signal connected to the input port of the cruise control block. This represents the difference between the desired and actual velocity. So if we check it, so here's the velocity and this one. So we could double click the signal name and name it as error because it represents the difference between your velocity and your specified or desired speed. Just you could adjust actually. So if you highlight some parts and then you could adjust it by dragging and dropping as well. Then you could just submit. So let's go to the next section. So we have a quiz here. So which of the following is true about Simulink signal? Signals contain data that can be constant or time varying. Signal flow is bidirectional. Signals are represented by lines with arrowhead. So among the three, the second one is false. So we could just identify it as a constant or time varying and it represents as an arrow, but it never be bidirectional. Okay, so let's go to the next. Chapter are we? Tripadine. Okay. So let's skip this part. It's just an introduction of the low pass filter or signal inspections. So I'll show you as we go along with the examples. So we have the set of, again, input and then a process or a system. So what we are asked to do is to add a display block to the model, connect the unconnected signal to this block. This is filters output. So we're going to add a display block first. Basically, this is to show you how we could simulate in model, right? So if we go to step, so at time 0, we have a value of 0. And then every time it has a 0.2 seconds interval. So every time we'll be able to check what is the value, right? So it is possible since we use a signal of time varying input, and every step you'll be able to check uh, what the operation the what operation value is at a certain timing. So as you can see here, until we completed the simulation at 10 seconds. So let's just continue this one. Then we could submit. Then we could next. So now instead of using the this display, we're going to use the scope. So this will show you the signal representation of the system. So this is basically this is just to show you the output of the system. So how we could use the sync part of our Simulink library. So this is just it could be any algorithm, just to show you the process of how we could check the output. Okay. So we could delete this one and then add a scope. And then you should see the filter. So we could set this one. And if we open the scope, we'll able to see the response. So at time 1 second, 2 seconds until 10. So earlier we used the display. It only accepts a discrete value. So if we run using or we simulate using the display block, you'll be able to get only the value at 10 seconds. But if you use the scope, you'll be able to see from 0 up to 10. So that's the difference between the two. So next is the scope accept multiple inputs allowing you to compare. So we're going to also to extend. So since scope actually accept many input value, we could also add signal here that we wanted to check. On this, they wanted us to check the noise signal. Just connect it here, right? Or here. So it depends on you. And then you could submit. So if we check, see, you could just go to the U and then legend. So we could see what is the noise signal. So the noise signal is the blue one, and the add here, add one, is the output. The output of the add block is the yellow one. And then you could go next. So label, the scope can have legends. If the signal are named, the legend will identify the signal using this name. So noisy signal has already been named for you. Label the other signal connected to the scope as a black filtered signal. So we're just going to label the signal as uh, filtered signal. Signal. Then if we open, you could go to view and add the legend as shown here. And then let's run. So as you can see, the name of the add block is changed to filtered signal since we already replaced the name of the block into some signal name, like what is represented here for the noise signal. So let's go next section.
As you've just seen, Simulink Scopes allow you to monitor signals in your simulation. Just like an oscilloscope, you can monitor signals while the model runs, as well as record data for further analysis. But scopes do more than just plot outputs. So let's take a look at what else you can do with them. You can inspect a signal in more detail using the zoom tools, including independent axis zooming. The pan and field tools also help you find what you're looking for. The scope display is customizable from the Configuration Properties menu. From here, you can choose to automatically open the scope with the model, or save the scope data to the Matlab workspace. You can also adjust the layout of the scope, for example, putting each signal on a separate subplot. Or, as we did in the previous exercise, use a single plot with a legend. As a reminder, legends take the name of the signal connected to the scope. Simulink's run and step buttons are also available directly from the scope tool strip. Stepping through a simulation can give you insight into what's driving the behavior of the model, and it's a useful troubleshooting tool. You can make common measurements on the signals from the Tools Measurements menu. If you have toolboxes other than Simulink installed, you may see additional menu items here. The cursor measurement window allows you to trace signals and estimate the period or slope between 2 points. If you want to share your simulation results with others, you can export the scope images using our print and copy functionalities. The copy to clipboard option adjusts the colors of the scope image to make it appropriate for including in other documents. If you want to know more, use the Scopes Help menu to access the scope documentation page.
Okay, before we proceed to our next discussion, okay, I'll just show you this one. Um, so in Simulink blocks, this is the most useful blocks in the Simulink library or in our library browser. So we have the math operation. This is the usually um, we use for the system creation, and then we have a logic operation that also used much commonly. So just to share. Go to the. We proceed to the chapter 4, mathematical operation. As you can see here, we have input already. So a new type of source has been added to the model. This is a ramp. It output a signal that increases with a constant slope. So the slope is 2. Compute the square root of the ramp signal by adding the square root block. So we're going to use the square root block. Then we will going to connect it to the our input. Connect it to our signal assessment. Since we're just asked to get the square root of the value of our input. And then submit. show you how we could get the square root, or we have the square root block that we could use. Then, in addition to time varying source like the sine wave and ramp block, Simulink contains a constant source. So you could add a constant block. So constant block can be represented as discrete value, or if you want to add signal on it, you could later on, it will be shown. So in these examples, then you could change the value, double clicking the block, and then just, um, input the discrete value that you wanted to add. For this time, we are asked to put 3, and then connect it to the signal, to the new signal assessment. So you could submit. Mathematical operators operate on the value of 2 or more signals and the output result. So these blocks will have multiple input ports and 1 output ports. So the order of operation is usually from top to bottom. So place a subtract block in the model. And let's get the difference between the ramp signal and the constant number 3, constant value 3. What we're going to do is that connect it here. We just add to subtract and then connect it on the minus sign. Process of the operation of how we compute addition or subtraction is just the same. It's just that it is represented in terms of blocks. Let's submit. And let's proceed to the next task. Task is to amplify the previous result by a factor of 2. So in order to amplify the operation, we need to add a gain block. So just gain. So I'm just typing in the gain block. So as I mentioned earlier, you could access it in the library browser as well. And then it wants us to amplify the operation by factor of 2. So double click and then change the value to 2. Then we're going to add it to the end of the operation. Here. Then you could submit to the next task. If it's about basic logic, open here. Okay, okay. So we're really on a basic logic topic. And now we're going to use the logic blocks. This is part of blocks or operation for logic that I introduced to you earlier. This is something that is always used whenever model is created, especially the math operation. So that is the common, because it is the easy way to represent your equation or your algorithm or even the codes. Then we're asked here to add a compare to zero block. And ask us to change the operation as block them, change the operator to the greater than operator. So we're going to change it as a greater than operator. So just double click the block and you'll be able to access the operation that you wanted to implement. Just connect it, our input, and then our assessment signal. Proceed to the next task. So we are asked to copy and paste the sine wave. So this process is just showing you how you could use the conditional operator or your logical operator to assess the information of your input. So basically, it's just comparing the value of the sine wave to zero and then checking the output. Then copy and paste existing. Change its frequency to 2 rod per second. We're going to change the frequency to 2 rod per second. We're going to add a compare to constant block. Compare to constant block. I'm going to connect this one here. And the other side to the signal assessment. So we're going to set the parameters such as the block output 1 and signal is greater than or equal to 0.1. So greater than or equal to. So in case you wanted to compare your value to a certain constant, you could do this by using the compare to constant. The other block, the compare to zero, is just to use if you want to compare your value to a value of zero. Now we're going to add a logical operator block. So we're going to add a logical operator from Simulink, and then we're going to compare value of our first signal to our second signal since it is already represented by a logic value, right? 0 or 1. So this one also already contained that. Proceed to the next process. Ano ba to? Conditional statement. So we already explore the different types of logic blocks. So now we're going to conditional to discuss conditional statement or give an example about conditional statement. A conditional statement can be expressed using the switch block, which exists. So it represents if-else statement. The second input is the condition. The first input is also a condition, and the middle one is your output. I mean, your true condition, your true value when the condition are permitted, and then your false value in case your condition is not permitted. So let's use switch block here. So like other blocks, you could also change the size of the switch block, connect the sine wave here. And if the condition is permitted, it will be the output. If not, then we use this one. Right, and we're going to connect it to our signal assessment. So signal assessment, again, is just a representation of your sync. So if you don't connect it to your output, it will give you an error. And we could submit. So the next task is to change the algorithm to the following using the step below. So instead of outputting a constant value, it will output the value of your condition. So we're gonna use this your input. So it is possible that you use the condition as your output once your condition is satisfied. So this is something that you could also apply to your model. Um, Another thing is that you could actually um, connect different signal or more than one signal on a single value. Okay, just next. So, and here the sine wave is greater than 0.2. So we're just going to change the value of the threshold. So we are already in chapter 5. So every block contains a help function, something that you could use. You could also go to the documentation in case you wanted to learn something, or for example, you wanted to check on something. So you could just direct here in the documentation, and for example, you want to check on Simulink block. So I search on a Simulink block and it gives me 12,000 results. So all the information about Simulink block is located in here. This is something that you could use in case you wanted to learn on something or you want to deepen your knowledge on a certain topics. Let's proceed to the 6. Basically, it introduced to you the signal or signal editor blocks. If you want to put signal scenarios, this is can compose of different test cases that you wanted to check. So if you want to check the capability of your system, you could do or create multiple test cases and insert it in your signal editor block. It accepts different types of files. You could use usually we could use Excel files or to input your what do you call that, your test cases. We go to the activity. Where it is. So here, as you can see, we have the sensor data here. It is actually your signal editor block. So as I mentioned earlier, you could add files here. So for this example, since a math file is something that is created in MATLAB, so this is the easy one that could be. So we're going to add an absolute value block for this one. The first thing that is being asked. Since we need to pre-process the input data, so we need to take the absolute value of the lateral acceleration. So we put the absolute value here. And then let's proceed to the next. The next one is application of the logic that we have here. So we have here statement, and we need to add compare to constant block since we have different value or varying values of speed here that we need to check. So compare to constant. Right. So we're just using this example to implement the model. So it asks us to add 3, compare to constant. Then we change the value. So greater than or equal to 100. Greater than or equal to 35. And the last one is greater than or equal to 3. Okay. So connect the block to their appropriate signal. So greater than or equal to 3 is related to acceleration. It already gave us an idea. And it mentions that speed is greater than or equal to 100 or speed is greater than or equal to 35. So these two constant compared to constant is related to this part. So we're going to connect it to our speed data since this is the information that we needed to check. And this one is connected to our lateral acceleration. Check and okay. So we already use our block for the constant, compared to constant block. And then we can now submit. Let's proceed to the next task. The next one that we need to do is to complete the process. So add a logical operator block to the model. So this is just the continuation of the if else statement that we are implementing. We just need to add an add block. Sorry, logical operator. And then let's connect the speed and connect the appropriate compared to constant block to create a statement. So we need to do this representation. So we just need to connect the speed compared to constant of 35. And then the lateral acceleration here, signal assessment. So we're going to connect it to the signal assessment. And our next task is to implement this part. So since this is already implemented, this is part of the if else or if statement or the condition. We're not going to add the or we're just going to copy this one. So let's just adjust the signal operator. Then it's a copy and then change it to or. Connect it to the speed comparing to 100 kilometer per hour. So this is the representation of that. And then we're going to connect this condition that we created earlier. This one, this is the representation in the model. And then we're going to connect it to the or condition. We're just going to extend the signal to our assessment block. Click submit. Then our next task is to add the output for each condition. So we already introduced to you, or I already introduced to you the switch block. So we're just going to implement that. So as mentioned here in the task, we need to add a switch block. We could just size this one. We have a two possible output value, mode 1 or mode 2. So we're going to use this one to connect here. Pero wala siyang sinabi. So add then connect the output from the previous task add to constant the value upon the driving modes connected to the block appropriate location of the switch block. So it doesn't mention anything about the threshold. So we just left it as is, and then we add the constant block to represent the output of your if else statement to apply and then put one here. Uh, that's it. Then before we proceed to the next task, let's have a break first. So let's have a 5 minute break. Where we are. So we're already in the middle, and let's have a 5 minute break for now. Sorry, I forgot to unmute myself. So, can you hear me now? Sorry, I forgot. So, I'll repeat what I said. So, it is about workspace variable. So, anything that represented by R, I mean, if you represent an information or a variable in a workspace, you'll be able to access that just by um, specifying the variable name. Like for this one, we have an amplitude of R. Then we apply and click OK. And this will work as if you specify the variable 5. Right? So our next topic is now we're going to add another block. This is a gain block. And then we're going to... Hello? Can you hear me?
Opo.
Okay. 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 So, so now we're going to add the block gain. So we're accessing a variable or a block that can be assigned a certain value. So if we open this one, we're going to add a my gain. This is a block name. If you so now you could see that we have a caution marker. So what you're going to do is that you could fix this one by clicking this part, the third dot here, and then create. So you specify the value. So you could enter the value here as 3. And then use base workspace. And then we click create. And now your gain block is already specified on your workspace. As you can see, it is already in our workspace, the my gain and the variable R. And if you just type in here, you could access the defined value of our variable. And same with the my gain. So if you open it or double click it, you could just do that. Be able to see or check the value. Let's go back to the next. We're going to change the amplitude of our my gain, of our sine wave into the value of my gain. We're going to my gain. And then could apply and okay. Submit. Okay. So let's go to the next section. So this is introduction of Matlab function. So later on, I'll show you how we could use this one. So I'll skip this part. Oh, to the problem. So what we're going to do here is that we're going to model the power output from a tidal turbine over the course of this topics or chapters. So we have the equation here. We have the representation of the power. So what we're going to do is that it asks us to use the Matlab function. So what we're going to do is that we're going to add here the anong tawag dito? Formula of the power. We're going to represent or this formula in your Matlab function. So in case you have a complex algorithm that you think you could represent it in terms of or much easy to represent in terms of a formula, then you could use a Matlab function. So this is another way of how you could represent a system or a function. So our delta H is represented by variable delta H or this representation. So I just type in 0.5 multiplied by, so we have the representation of power coefficient, CP, by CP, and then, so this is already declared. As you can see here, this is a declaration of your variable. So once you run this function, you'll be able to define this one. So no, that's why you don't need to put it in your, what do you call this, workspace separately. You just need to run this function, and this will be added to your workspace. So that's why you could represent your variable as its name or its equivalent name. Just multiply 2 times g. So I'm just using the constant or the variable that is defined in the upper part. By absolute value of this must be inside. Delta H, raise this part to the value of 3 divided. And then we'll just go back here and connect it to our signal assessment. So let's check why it has an error. I forgot some. Okay, because I don't have row 1 or the density and specify. Double check. We have 0.5 and then the value of our coefficient and then value of density, area, and then multiplied part 2 times gravity times absolute value of delta raised to this one. I think it is correct already. So let's check again. Okay. Let's go to the next task. So let's proceed with, before we start with the dynamic system, let's watch the video first.
Engineering is full of dynamic systems. Dynamic systems have states whose values evolve over time. A state is just a type of quantity like position, population, that depends on previous states as well as other properties of the system. For example, states depend on conditions, physical characteristics of the system, and external inputs. System outputs, in turn, are dependent on the states. Discrete system. One of the states that's typically time constraint of one or in some systems, we model time as continuous. In other words, for that case, time between samples approaches zero. Since we assume input test is all time steps, continuous dynamic systems are described by differential equations. Computation will keep track of the derivative of our state instead of the state itself and integrate it each time step. Signals carry the values of states like position and velocity, inputs like gravity, and outputs over time. As always, blocks allow us to express the relationships between signals. In the next lesson, we'll learn how to express the relationships to model dynamic systems.
So let's proceed with the next topic. So discrete system. Let's go to the problem. Right now, we are asked to add a sine wave to the model. So let's double click the block and add sine wave. Then we're going to change the sample time of the parameter to 0.5. So this is just to show you that you could also implement the changing value of the sample time of your system, I mean input, rather aside from changing the sample time of your simulation. So you could also use this one. It already. Sample time. Please use. Kaya pala. Okay, so we already specified the sample time. Click submit and then let's go to the next task. So we're going to add the unit delay. This is to hold the value of our input. So we could use this on the next step as well. So you could add unit delay. Delay. Send unit delay and send the delayed signal. So we don't have any value to specify. Just click next. Now, difference equation are expressed in terms of time step, okay, and the length of the delay. The current state is x of k, which previous states being x of k minus 1, x of k minus 2, and so on. So we're going to specify the signal to our unit delay as x of k. Then we're going to specify the signal from unit delay to our signal assessment as x underscore k minus 1. And then we're just going to submit this one. So compare x of k and x of k minus 1 by connecting both signal to a scope. So we're going to connect them both on the scope. See the response. Why do we miss something? Compare connecting both signal to scope. Turn the legend on its side. Okay. So we didn't turn on the legend. Legend, view, and then turn on the legend. If you can see here, so the yellow one is your x of k minus 1. So the response of this is delayed by one step in compare to your x of k, which is what we are expecting, right? Let's go to the next step. Double click on the unit delay block and set the sample time to 0.5. Unit block time to 0.5. So let's compare again what will happen to the signal. Okay. So as you can see here, the delay becomes almost double. This is because -1 represents that you are just implementing the times or sample time of your x of k. But right now, since you already specify a value of 0.5, you doubling the sample time that you have in your input. So let's proceed to the next task. For 10. I forgot some. Okay. So we'll skip this one and let's do the continuous system. So for that, let's open this the presentation first. So this is just a discrete. So you already heard about this one. So how you could connect, how you could use the unit delay. So the next one is the continuous system. So to represent this variable or the value changing with time, we do integration. So in here, instead of using the delay, we gonna use the integrator block. So this is how it could be applied. This is just an example. So I'll show it to you in here para mabilis tayo. Practice. So the next thing that we will do is that we're going to add an integrator. So this is integrator symbol represent the integration in the Laplace. So we're adding integrator block to integrate the ramp. Is parabola. The original source is, so this is our formula, I mean equation that we wanted to represent. So we're going to use the integrator block. Integrator. And we're going to connect this one. So in this set of tasks, you will model a thermal system. The state of interest are the temperature T and the first derivative of temperature T dot. So delete the ramp block. We're going to delete the ramp block and represent this one as, so the signal entering and leaving the integrator will represent T dot and T. So this will be our derivative T dot underscore dot, and this will be our T. So this is the derivative, and then we pass it to an integrator. So we're getting the value of T. So we already deleted the ramp, and then we specify the signal. So here we have the Newton's law of cooling. So this is the first order and ordinary differential equation. So we'll model the right side of the equation, this one, in two parts. So we're going to start with the expression of T minus T sub 0. So we're gonna add a constant block to represent our T sub initial value of T, constant block. So we're going to set its value at 300. And then, so we're going to subtract the given information. So we have the value of T and our T sub 0. And then we're going to submit. And let's go to the next task. So now we're going to add again. We're going to add again block here. Gain block. Add again block to create the expression negative R. So we're going, since we already specified the R value earlier, it's going to use negative R. And then move this away. Connect. So connect the two signal represent T dot to create the equality. Connect the temperature signal T to the signal assessment. So we're going to connect this one, this one. And then we're going to connect the R to your T dot. To represent or finally represent the whole equation. Right? So this T dot is represented by your dt over dt. Ito yun. And then you have here that time here, and then your initial value. And this is the um, operation for this part. And then you click submit. Then we next. And now we'll go to the task 6. Open the block parameter dialog for the integrator block, and set the initial condition to 320. So this will be the initial value of your T. And then let's click submit. Go to the next task. So here we're going to proceed to 11. So basic signal processing. So the basic application of signal processing is Simulink is modification of simulation time and step size. So Simulink know how to assess the properties of your system and automatically select a good solver for you. However, it cannot determine how long your simulation should run. For example, these are the two systems below. So in order for you to capture the interesting behavior, so you have this slow system at your left, and it should be run for more time, and the fast system for less. So let's go to 11. Oh my God, 38. So by the way, in case uh, we are just left with projects, so actually you could do it without my help or without showing it to you, because it's just a application of this one. In case we wouldn't be able to tackle, you could do it on your own. But I will try to cover everything. So let's proceed to the 11. So we have here the behavior of double mass spring damper. So it's already modeled for you. You can inspect the behavior using the included scope block. So we're going to change the simulation stop time of the system to 20, so you can see additional dynamics. So let's change the stop time. 20. Submit. And then we could check on the response. So you can see here. So it captures all the important information that it has before it reaches steady state. So if you are checking something, so it's better to just occupy or specify here the time that you wanted it to be shown, or the simulated part that is your target. So you could only capture the important information and just ignore the other. So let's go to the next section. So I think it will cover everything. Let's do the practice. So it's just, do I have a PowerPoint? Okay, so let's go to the chapter 12 for the practice. What is this one? Next. So let's skip the quiz. That's really important. Let's go to the practice. So right now, we have task here. So the equation for the discrete PI controller. So you have a control system here. The design variable KP. We have here the KP and KI, and the sample time is TS. So this has been defined in Matlab Workspace already. So all the variable here are already defined. No need to do it. So we're going to build the signal for y sub I. So this function, and combine it with the existing signal for yp of k to create the controller. Okay, look at it. So, my God. Wait a moment. Give me a second. Okay, let's proceed. So what we're going to do is that we're going to add another gain block. But let's make it bigger. And then we specify the value of ki times ts. So you could directly input it here. Yes. And then apply. And then what we're going to do next is connect it to the KP. This part. So branch EK. No, not KP, sorry. By the signal EK, what I mean. So branch EK and connect it to the gain block. You just you just created. So you're just gonna connect it here. Next is to create the term KI TS EK. So we already have KITS and EK, E of K. So we could just submit this one. The next task. So we're going to add the appropriate number of unit delay blocks to the model to represent the integrator term y of I k minus 1. So since we only have k minus 1, we only need a single unit delay. Delay. Here's something that we will use later on. So mga to yun. So let's create a stub on the unit delay block, and then we'll label the appropriate signal as yi of k and yik minus 1. So what it wanted us to do is just to extend the input and output part of your unit delay. And we input a signal here of y, I, k, and then we have yi underscore k minus 1. And then, so that's what our task is expecting. So let's just next. So this is just to represent the y of k and then the delay value of yik minus. Let's do the next task. The next is what we're going to do is we're going to connect the KITS and the this value. So so I'll just bring it down and then to just to make a space and then add a signal block, add block, add block. We could extend and then let's connect it here. So we just connect to represent this equation. So to represent this part of the equation, we just connect the yk of yi of k minus 1 and then the add the value of kits times ek. So since the signal is multiplied with this kits, then let's proceed to the next task. So the next is make the connection that completes the integrator equation y of I of k. So to do that, we're just going to connect the add part to your signal. So let's remove this part. So add this to the addition part or end of the add part of your equation. And then to represent yik, so this will represent the whole system. So we're going to connect this in this part. So since this is the equation of yik, so as you can see here, it is represented by kits and times ek. And then we have added this part with k minus 1. So this is the representation of yi minus k minus 1. And then added part is here. And then we're going to just represent this one. So our next task is to add the signal yp of k and yi of k to create yk. Ito. This part. So connect yk. So we're going to connect the yk. Where is yk? Let's see this one kung anong laman nito. This is the yp of k and then this is the yk. We're going to get the value of yik and the ypk. So we're just going to add both of them. All right. Going to add both. So just gonna create add block here. This signal. Add it. Get it and add it here. And add a signal here to create the YP. And then we're going to use this one because this is your YK. Try this first. So we represent the YP and the YIK. Connect the input of the house subsystem. Ito pala. So we're going to import this in the house of here. So we're going to output the YK here. And then connect it here. The system. And the next is to set the sample time of TS. Use the default initial condition of 0. Sample time of TS. Yes, where is our TS? So we're gonna use the sample time here of YK. And then okay. Kaya pala, initial condition difference. Okay, apply. Then we submit. So next is next project. We have for the 13 part. So this is the project Peregrine. So you could just do it on your own. So it could be your what you call that activity. All the discussions that we had from chapter 1 up to chapter 11 are being applied here, like I shown you on the chapter 12. So we cover it already. And there is another one, which is 13. Actually, the 14 is none. It's just a conclusion and survey. But the process and the learnings that already discussed from chapter 1 and 11 will be applied in here. Same as what we did in the chapter 12. So again, I think that's all. Do you have any question?
Ma'am, may question po ako sa chat box po.
Ay, sorry, hindi ko napansin.
Okay lang po.
So working samples po ba?
Actually, yung mas nauna. Yung about sa code generated ng algorithm sa Simulink po. Kung nakikita po ba yun? Na-access po.
For example, you wanted to co-generate yung generate mong model or system?
Opo. Bali, kasi po di ba pag po, parang ang intindi ko po yung Simulink ay nagpapadali siya nung, instead na i-code mo siya all manually. Bali, basta alam mo yung algorithm, ibubuin mo na lang yung functions para kang nagbubuo ng flowchart. Pero it is limited. It is limited, I think. So you need to learn yung Matlab, yung coding pa rin sa Matlab na main. So
Okay.
in case na ma-encounter namin, for example, ay parang hindi kaya ni Simulink. So kailangan namin pumunta doon sa Matlab na main. Pwede bang mapadali yung task by just copying yung code generated nung algorithm doon sa Simulink, tapos ilagay na lang namin doon sa main program namin. Just like yung if familiar po kayo doon sa macro ng Excel, pwede pong i-play tapos i-access yung code tapos i-copy and then i-modify para mag-fit po doon sa main program ng VBA. Something like that po.
Si Simulink kasi meron siyang iba-ibang application. So, if we go to the main, wait a moment. Yes. I'll just going to exit with the Simulink link app. Let's open a model. If we go to the application, we have actually embedded coder. I think if you have license for, you could access all the application, right? I believe. You have the capability to do that. So if you have the Simulink model, you could use embedded coder to generate C++ code actually. So that's something that you could use, and this is already compatible with other IDE. So kahit saan mo siya gamitin. Pwede mo siya gamitin using the Visual Studio or any other platform actually. And kapag naman sa Matlab, if you code using yung Matlab, for example, hindi siya ma-code or hindi mo siya ma-create yung system using Simulink, and mas prepare mo na mag-code using Matlab, we have also Matlab coder na pwede mo siyang i-translate. Pero if ever na ang gagawin mong function is something that is related sa or much inclined sa control system, much better kung gawin mo siya in Simulink kasi meron siyang, yung embedded coder kasi is may capability na maging compatible na siya sa MISRA C or in other programming compliant na siya sa mga standards. So, ayun.
Tama po ba? Yung algorithm po ng nabuo ko pong Simulink yung mapupunta po dun sa embedded coder?
O, balik.
Okay.
Okay
po.
Sige.
Salamat po.
Do you have any other question pa po? Before we end?
I think may question po si Sir Charlton Inaw sa chat din po.
Sige po, check natin. May way po ba na makita yung gawang algorithm sa Simulink? Like, I think same lang, parang medyo same kayo. So, parang pwede tayong gumamit ng embedded coder para doon. So, once you created yung Simulink mo, pwede mo na siya actually i-add and then kunin and then pwede mo na siyang i-add doon sa code ng BBA mo. If kung gusto niyo mag-check yung mga embedded mga coder namin dito, we have here. Actually, I think yung Hadoop ang pinaka-related. Nasaan ba? Embedded coder. Here. So, we have also for PLC. And I think yung if C or C++ code, you could use embedded coder. Kapag naman, asan yung Hadoop dito? Yeah, ito lang. So we have embedded coder for Simulink and then Simulink coder. We also have PLC for PLC coder and Matlab coder. Kapag galing siya sa Matlab file. Sige po. Yes po. Actually, we have add-ons here. So, if you open this one, pwede nyo po ma-access yung mga hardware ni Arduino or ni Raspberry Pi. So, may support package. Actually, I have wala na. Actually, if you go, and then kapag in-install nyo siya, actually, meron ako dito Raspberry Pi. Verify ko. Ay, nag-reinstall pala ako. So, you could access it here. Sorry, wala na pala. Nag-reinstall kasi ako. So, ito. So, you could copy support package. For Raspberry. So, you have support package for Raspberry Pi or Arduino. Sometimes meron sa ibang hardware, tapos sila yung merong Matlab support package that you need to download. But for this one, we have already for the Raspberry Pi and Arduino. And Pwede siyang patakbuhin ng Simulink. It is Simulink supported siya kami Matlab code. So pwede kang mag-Matlab code and then pwede mo siyang i-deploy sa system sa may hardware mo na rekta na using your add-on support package. Ito po. Actually, if you want, we could show you a demo for this one. Pero for now, you could ask Jelisa or to have something a demo for the MCU. I could show you one. Yan po. So, okay na po ba tayo? Wala na pong questions? Sige po. So, if you want to have an activity, pwede po inyo i-continue yung on-ramp kung gusto niyo pa pong may mga ano rin po doon, discussions and examples and naka-show na rin po actually yung mga what do you call that? Yung mga result if ever na hindi niyo siya makuha agad. So meron tayong mga parang support doon na included na po ng on-ramp. Ayun po. And asan ba? Self-paced training. Wait lang po. Let's show para makita niyo yun. Hindi lang. Matlab. So, as you can see here, marami po tayo dito na pwede nyo gamitin. So, if you want to learn yung online scripting for accessing the API layer ni Matlab, pwede kayong mag-Matlab on-ramp and you can continue to Matlab fundamentals para sa optimization. So, related na rin po kasi dito. And then yung statistical. And then we have also for data processing and visualization. Meron po tayo AI. If you want to apply AI, machine learning, so we have deep learning as well, and reinforcement learning. So, pwede nyo po to sundan, and then may process na rin doon kung paano siya, I mean, yung mga basic is nandun na rin. So, image processing, meron na rin po. So, you could work on this one. Kung gusto nyo po ng ibang topics, hindi lang sa control system. Yes po. Yes po. Okay na po tayo? Wala na pong question? Okay po, thank you. Bye po.
Salamat po.
Recording stopped.
All right. Thank you everyone for your time. I hope to see you po again on the workshop later 1 p.m. So we will be having the electrical simulation with Simscape. That is on 1 p.m. later. So we hope to see you there. Thank you very much po.